Alright, so welcome back. Let's look at the case 3. Let's look at the case 3. Very good. Now the case 3 is the characteristic equation has, or if the characteristic equation has complex roots. So if it's having a complex root, how are we going to do it? If it's having a complex root, how are we going to do it? Let's consider a second order differential equation. So we are considering this second order differential equation. Now when we write it in the characteristic form, which is lambda square plus p lambda plus k is equal to 0. And when you punch on your calculator or when you solve it, you get the lambda 1 to be this and the lambda 2 to be this. Don't forget that the lambda and the beta there, they are all constants. They are all constant. Alright. But we are using this to generalize it. Very good. And with these two solutions, you can write it as lambda 1, comma 2 is equal to lambda plus or minus beta I. Very good. So you can see that here we have the imaginary number and the real number. Very good. Very good. Alright. So when you resolve with this solution, please don't forget that this is the same as 2 plus or minus, let's say, square root of 3i. Or 2 plus or minus 3i. When you get the I in it, yeah, it means it's a complex root. You are not saying that since it's the I which is making it a complex root, not like getting 2 plus or minus square root of 3. When you get 2 plus or minus square root of 3, this is not a complex root, but this is rather a complex root. Alright, we can get this place to be 5 or square root of 5, it's still a complex root. But if you get this place to be 5, it doesn't make it a complex root. It's just a distinct root. It's just a distinct root. Alright, yes, it's a distinct root because lambda 1 is 2 plus square root of 5. Lambda 2 is 2 minus square root of 5. So please be careful with how to differentiate between this and this. They are not the same. Alright, so if you want to write a general solution, then we need to go and identify lambda and identify beta. So for instance, if you have 2 plus or minus square root of 3i, the lambda is going to be 2 and the beta is going to be square root of 3. So for you to write a general solution, then this is going to be the general solution form. Alright, now we are going through some process, but I don't want to be doing those proofs to you. Alright, when you prove from Euler formula, when you prove from Euler's formula, when you prove from Euler's formula, this is what you are going to get for your answer. Very good. So this is a general form of writing a characteristic equation that has a complex root. Alright. So when you come, your lambda will be here, the value of your lambda will be here, the value of your beta will be here, and that is all. Alright? Hope you can see it's not difficult. It's not difficult. Alright, and that is all. So for instance, if this is our solution, the lambda is 2, the beta is square root of 3. Then you go and do your substitution to the general equation. Alright, in some books, they will bring K1, K2. It's still a constant, it doesn't matter. Very good. Very good. Alright, so let's look at our first question. Determine the general solution of the equation. Determine the general solution of the equation. The square y over bx squared minus 6 Alright, so this is a second order differential equation. So let's go and write the characteristic equation. In fact, this is the same as y prime minus 6y prime plus 25y is equal to 0. Alright, so to write the characteristic equation, we are going to get lambda square minus 6 lambda plus 25 is equal to 0. Alright, so with this, your small calculators can support. Alright, so alright, so now you can see that we are resolving at a complex root, and the lambda 1 is 3 plus 4i. The I is making it a complex root. Lambda 2 is 3 minus 4i. Alright? Therefore, lambda 1, 2 is equal to 3 plus or minus 4i. I hope it's clear. Very good. So, then after that, we go and write our general equation. So for you to write the general equation, it's still not difficult. We come back. Then we write e raised to the power lambda. What is lambda here? So the lambda here is representing the 3. Okay? And the beta here is representing the 4. Very good. So now that we know the lambda and the beta, please don't forget that the beta is not negative 4, but the beta is rather 4. Very good. So we come back to write the general equation. Lambda is 3. Beta 4. Sine beta, which is 4. Alright, so this becomes our general solution or general equation. Why is this a general solution? Because of the constants introduced. Alright, now for you to be having a particular solution, then you need to be given the IVP. And since here is a second order differential equation, there will be 2 IVPs needed. In fact, as time goes on, we will look at such question and see how that is going to be. Very good. So let's look at our next question. Find the general solution to the equation, or determine the general solution to the equation. What is the solution corresponding to the initial condition? So now here we have an initial condition y0 equal to 3 and y prime of 0 equal to 3. It means that we're going for the particular solution. So it's not difficult. The characteristic equation will be lambda square alright, so the result lambda 1 comma 2 will be negative 1 plus or minus I. Negative 1 plus or minus I. So our alpha here is going to be negative 1. And the beta here is going to be, tell me, 1. Very good, not negative 1. 1. Alright, then we quickly go on to write the general solution. Write the general solution. So the general solution, lambda is negative 1. Very good. So negative s, c1, cos beta is 1. Beta is 1. But the argument here to be the same as the argument here. Very good. So getting this up here is not difficult. Alright. So that's going to be our general solution. So for us to work using this IVP, you can see that y of 0 is equal to 2 means that here you are doing the substitution of x to be equal to 0 into the function, into the general function, and equate the y to be equal to 2. Here, y prime means that we need to go and differentiate this. We need to go and differentiate this to get the y prime or the first derivative before we can do the substitution. And that is how that is done. Very good. So let's go through the process to get that. So first of all, we can do the substitution of y of 0 is equal to 2. So this means that you put x to be equal to 0, y to be equal to 2. So we get 2 is equal to e raised to the power negative 0. Wow. Any number raised to the power 0 is 1. C1 cos s cos 0. Alright, so with this substitution done, we are going to get 2 is equal to alright, so to get C2, so we get C1 to be equal to 2. Now after getting C1 to be equal to 2, since the second initial condition, y prime of 0 is equal to 3. So we need to go for the first derivative of this one, general equation. Alright. And how do we do that? To go for the first derivative of this, wow, you can see that here is going to be, we have one function here, another function here, b multiplying. And that's going to be a product rule. So y prime of s is going to be equal to, leave this, differentiate this, or we can leave this and differentiate this. How we can see that? Very good. So when we differentiate this, we get negative. Then we leave the second one. Plus, so leave the differentiate this. Now we are going to leave this and differentiate this. Alright, so to differentiate this, it's not difficult, let's go for it. That is a constant, so leave it. So you leave this constant. Now when you differentiate cos, you get negative sign. Don't forget, it's not sign, but rather negative sign s. Inside of a bracket, don't worry. Plus the constant, you can leave it. But when you differentiate sign, you get cos. Very good. Very good. So that is that for that. Very good. So this is the first derivative. This is the first derivative. So we can still go and factorize everything and whatever. We can even simplify it, but let's go and do the substitution. Alright, now we know that the y prime is equal to 3. So this is equal to 3, which is equal to, when you see s, put 0 there. So we are doing substitution. Alright, so that is that for that. That is that for that. And this will be simplified to 3 is equal to negative C2 plus C2. Sorry, negative C1 plus C2. But we know C1 is 2. So by substitution, negative 2 plus C2, then C2 equal to 3 plus 2. Alright, so C2 will be 5. So we get C2 to be equal to 5. So now, we can now go and write the particular solution. We can now go and write the particular solution. Alright, so therefore, the particular solution e raised to the power negative x. Don't forget. So the C1 is now 2 cos s plus C2 is now 5 sin s. Alright? Very good. And that is all for that. So this is going to be the general solution. Then the other one is going to be, this is going to be the particular solution. And the other one is going to be the general solution. Alright. I hope it's clear. Very good. I would like us to add one more example, then we proceed to that of characteristic equation that has a complex root. Still under case 3, let's look at the last example. Find the general solution of the equation that. Now, don't forget that this general equation or this differential equation is of order 4. Is of order 4. So, if let's say we are to be given an IVP, it will be the IVP for the function itself, the IVP for the first derivative, the IVP for the third derivative, and the IVP for the fourth derivative. So, an example like this, for you to get the particular solution, you need 4 IVPs. Very good. So, first of all, the first thing to do is to go and write it in a characteristics equation. So this is the characteristics equation. Alright, very good. And when it's algebra, when you solve it, so by solving, we are going to get, or by factorizing, you are going to get lambda square minus 4 lambda plus 13 all square. Alright. So now, what this means is that when you punch this on your calculator, and now if you are using some of the TI-84 Texas instruments, you can punch the whole of this on your calculator and you get your final answer. If you don't have, then you need to use your algebra to simplify it to this form. Now when you simplify to this form and you punch this on calculator, only that, on calculator, you are going to get lambda to be equal to 2 plus or minus, you are going to get it 2 plus or minus 3i. 2 plus or minus 3i. This is telling you that the I there is telling you that it's a complex root. It's a complex root. But here, be careful, because here, what this means is that the square here is not affecting this now. Also, don't forget also that we are dealing with fourth order, so the root is supposed to be 4. But with this, we have only 2 roots. The first one is 2 plus 3i. The second one is 2 minus 3i. But don't forget, when this simplifies to this, we get all our 2. So what this means is that any solution that will come out from this is going to have a multiplicity of 2. It's going to have a multiplicity of 2. So this will be having a multiplicity of 2. And this is also going to have a multiplicity of 2. Very good. So this can be the solution for 1 and the 10. And this is going to be the solution for 2 and the 4. Okay? Very good. So that is going to be the solution. Multiplicity of 2 here, multiplicity of 2 here. Getting 4th root. Very good. Very good. Alright. Then we can go and write our general solution. We can now go and write our general solution. Alright. So to write the general solution, please watch. It's not difficult, it's just simple. Same idea. Now in this is going to be the alpha, this is going to be the beta. The same for this. So alpha is 2, beta is 3. Alright. But this is having a multiplicity. So don't forget the case 2. Don't forget the case 2 here, because it will be in need of it. You will be in need of it here. Very good. Now, before we write the general solution, I would like to show you something. This having a multiplicity, so writing it is going to be somehow different from the normal way that we know. So before that, this general solution, let's not simplify it, but let's expand it. See, this and this, we get C1 e raised to the power lambda x. Then here we are going to get cos beta s plus, I hope you can see from the board, e raised to the power lambda s. Let me bring it down for you to see it well. So we get C1 e raised to power lambda s cos beta s. Alright. Note that this is the same as this. Very good. So, for us to write the general solution of this multiplicity, then that's going to be just simple as this. So the first one, the lambda here is 2, then beta is 3. Okay? Very good. Alright, so now let's go and write. So the general solution is going to be equal, please watch. It's going to be equal, don't forget that here is a multiplicity. Alright, so we need to introduce another constant here. Okay, very good. So I'm going to group this constant and call it C1 plus C3. Oh, somebody can choose to make it C2. But if you make this 1, 2, then you have to change this to 3, 4. Depend on you. But I would like to leave it like this: C1, C3. Then that multiply E. Please, I'm coming. I'll be doing something. The alpha is 2s cos beta is 3x plus. Now here, that one is going to be C2 plus C4. Beta is, alright, the beta is 3s. Very good. Please watch. Don't write it now. This is different from the one that you get it. Alright. Very good. So now, after you are done, then you come back. Then after you are done, this is what you have for now. Very good. Now after you are done with this, then you come back. Oh, this is having a multiplicity of 2. This is having a multiplicity of 2. Then, like how we write that of a characteristic equation with repeated roots. Then you come and attach s to the second constant. Here, you come and attach s to the second constant. And that is all. I hope you can see that. It's not difficult. It's just easy as that. Now, watch something. Since we have e raised to 2s here, we can go and factor e raised to 2s out. But don't say that we have argument of 3s here. So we can factor the argument of 3s out. No, you can't do that. But you can only factorize e raised to 2s here. Alright? And that is what that is going to give you. Very good. So that is how we go through the characteristic equation that has a complex root. Very good. In fact, in our next video, we'll be looking at Cauchy-Euler equation. Don't forget, all the solutions that we have looked at it right now is homogeneous linear equation with constant coefficients. So the Cauchy-Euler equation is the same as an equation with a variable coefficient. Yes, that is also going to be that is also going to be a homogeneous equation. Alright? But with this, it's going to be of variable coefficients. Don't forget, we are looking at higher order differential equation 1. The two talk of the same thing. but for that one, it's of different concept. Thank you.